In this video, I want to continue on with our examples of finding equations of planes. So let's start with number 6. Find an equation of the plane containing two intersecting lines, x equals to 2t, y equal to 2 minus t, z is equal to 3 plus t, and x is equal to 1 plus t, y equals 2 minus t, and z is equal to 3 plus t. So we're finding the equation of the plane containing two intersecting lines. Well, we can do this by finding the equation of our two vectors. So we have a vector u, which is 2, -1, 1. This is a vector in the plane because that line is in the plane. And we have the vector v, which is 1, -1, 1. Okay, so now we have two vectors that are in the plane. And again, we can just take their cross product. So let's do that now. So we take the cross product of those two vectors, which was, our two vectors were 2, -1, 1, and 1, -1, 1. This gives us the vector -1 times 1 is -1, minus -1, minus the vector, let's see, 2 minus 1, and then the vector -2 minus -1. This gives us the vector oh, no, it's a 0. Then -1 and -1. All right, so we got the vector 0, -1, -1. All right, let's go ahead and rewrite that out up here, 0, -1, -1. And that is our vector normal to the plane. Now we just need to find a point in the plane. So how do we do that? Well, we need a point that is in both of these lines. That means we want x to equal x. So if we want that to be the case, then we need 2t to equal 1 plus t. We need y to equal y. So this is 2 minus t is equal to 2 minus t. That's correct. And then we need 3 plus t to equal 3 plus t. So we want to find some t value that makes all three of these statements true. Well, the second and third are true for any values of t. So really, we just want the first equation. We just need to find a value of t that satisfies that equation. So 2t is equal to 1 plus t, or in other words, t is equal to 1. If we plug in t equals 1 into either of these equations, we will get the point 2, 1, 4. This gives us a point that is in both lines. Really, we just needed a point on any line. So in fact, we didn't even have to do all of that work. We could have just plugged in any value of t and gotten any point on either of those lines. But we saw how we could find an intersection point of two lines here. Okay, so if we have that as our point, and then we can find the equation of a line, or of the plane now. So how do we do that? Well, that is 0 times x minus x naught. And this is plus a -1 times y minus 1 plus a -1 times z minus 4. is equal to 0, or in other words, negative y minus 1 minus z minus 4 is equal to 0. Now notice, this is actually equivalent to this equation over here. Notice that this one here is negative y plus 2 minus z plus 3 is equal to 0. Or in other words, negative y minus z plus 5 is equal to 0. And then go ahead and simplify the other one as well. Let's go ahead and simplify this one. So we'll clear that out. And that equation was here. So this is negative y plus 1 minus z plus 4 is equal to 0. Or in other words, negative y minus z plus 5 is equal to 0, which is equivalent to what we just wrote here. So either of those solutions would be correct. And of course, there are actually infinitely many solutions to this. There's only one plane, but there's just infinitely many ways to write the equation of that plane. All right. Let's move on to some more examples. So example 7 here, find an equation of the plane containing two parallel lines. Well, we need to find a vector in the plane, so we can do that by just taking the vector 2, negative 1, 1. And furthermore, we need to find another line in the plane. Well, we can plug in x equals 0, excuse me, if t equals 0 into both of these parametric equations for the line. If we plug it into the first one, we get the point P is 0, 2, 3. And if we plug in t equals 0 into the second one now, we get q is 1, 2, 3. All right. So then we get the vector pq. So the vector from point P to point Q, right? P and Q are in these two lines, which means they're in the plane. So if these 2 points are in the plane, then the vector PQ is in the plane, and this vector is 1, 0, 0. So now we have 2 vectors in the plane. So what can we do? We can take the cross product of those 2 vectors. So we wanted the determinant of I, J, K, 2, negative 1, 1, 1, 0, 0, which gives us the vector 0 minus 0, comma, negative of 0 minus 1, comma, let's see here, that would be 0 minus negative 1. Or in other words, we get 0, 1, 1. Okay, that vector right there is perpendicular to both of, or sorry, it's perpendicular to the plane, i.e. it is a normal vector to the plane. So we can use that to plug it into our equation for a plane. And we in fact get a times x minus x naught. Well, a is 0, so we don't get an x minus x naught term, plus b, which is 1, times y minus 2, just for our point 0, comma 2, comma 3 that was in the plane. All right. So that ends that example. Let's find an intersection point of the line. X equals 2t, y equals 2 minus t is equals 3 plus t, and the plane x plus y plus z is equal to 1. All right. So if we want to find an intersection point of this line and the plane, well, we could just plug in each of these into this equation. So if x is equal to 2t, then we get 2t plus y, which is 2 minus t, plus z, which is 3 plus t, all equal to 1. So this is 2t minus t is 1t plus t is 2t plus 5 is equal to 1. So t is equal to -2 here. If t is equal to -2, then we can just plug that into these equations here. If t is equal to -2, then x is equal to -4. Y is equal to 2 minus -2, which is +4. And z is equal to 3 minus 2, which is 1. And that gives us the point -4, 4, 1. Clearly, this point is along this line because we just picked any t, which was -2 here, plugged it in, so that point has to be on this line. If you want to confirm that we did everything correct and that this satisfies this equation, then just plug in x equals -4, y equals +4, and z equals +1 into this equation, and you will notice that it works. All right, so there's the end of that one. We got one more example for this video. And we want to find parametric equations for the line of intersection of these two planes, x plus y plus 2z is 1, and 2x minus y plus 2z is equal to 1. Whew. Okay. So we want a line of intersection of these two planes. First off, as long as two planes are not parallel, then their intersection will be a line. So how do we do that? Okay, this is going to take a little bit. All right, so we have some vector v. This is gotten from 1, 1, 2. This is a vector that is normal to this plane. We have a vector 2, -1, +2, which is gotten from here to -1, 2. This is the vector that is normal to this second plane. Now we have two vectors that are normal to each of these planes. Think about what that actually means. If they're normal to both of these planes, then we take a cross product of these two vectors. If we take a cross product of these two vectors, we get a new vector that is orthogonal to both of these vectors. If they're orthogonal to both of these vectors, that means this new vector lies in each of these two planes. So if it lies in each of those two planes, then it is a vector that is parallel to this line of intersection in these two planes. So let's take the cross product of those two vectors. So v cross u here is equal to the determinant of I, j, k, 1, 1, 2, 2, -1, 2, this is equal to, skipping a few steps here, this is the vector 4, comma 2, comma negative 3, and this is a vector in both planes. Okay. Now we just need to find a point that is in the intersection of those two planes. So how do we do that? Well, we have a couple ways we can do this. One, we can start just by guessing that maybe x equals 0. So we have a point 0, something, something that is in both of these planes. And in fact, that is very, very likely. The only way it doesn't happen is if this line is parallel to the x equals 0 plane and not x equals 0 itself. So let's check that. So if we plug in x equals 0 here, we get y plus 2z is equal to 1. And we get negative y plus 2z is equal to 1 as well. Just plugging in x equals 0 into those two equations of a plane. All right. Then we can try to solve these two values here. If we do that, we can just add these two equations. We get 0y plus 4z is equal to 2. Or in other words, z is equal to 1/2. Okay, so we got z equals 1/2. Then we can plug that into this first equation. X was 0, z was 1/2. That tells us we get 0 plus y plus 2 times 1/2 is equal to 1. Or in other words, y is equal to 0. Notice if we plug this into the other equation, so 2 times x is 0, 2 times 0, right? We said x was 0 here. 2 times 0 is 0, minus y plus 2 times 1/2 is equal to 1. We get negative y is equal to 0, or in other words, y equals 0 again. So we do in fact see that the point 0, 0, 1/2 satisfies both of these planar equations. Now going back for a few minutes, we said, let's just assume x equals 0 for a moment. Well, it turns out that if x was equals 0 gave us some kind of contradiction when we tried to finish out this system of equations. Then we could just try y equals 0 or z equals 0. One of those will work. So you could just keep trying one of those, and eventually one will work. Here, x equals 0 did. In fact, we could have done that for choosing x, y, or z to be any point that we wish, or any value that we wish. If the system of linear equations ended up working out, which it did in this case, then all will be fine, and it almost certainly will. Again, if it doesn't, just pick another point and value, and you will be good to go. Okay, so what we have found is that this point here, 0, 0, 1/2, it lies in both of these planes. And we also found that the vector 4, 2, negative 3 was the vector of this line, or the direction vector for that line. So this gives us the parametric equations. X is equal to 0 plus 4t. Y is equal to 0 plus 2t. And z is equal to 1/2 minus 3t. And those are the parametric equations for the line of intersection between those two planes. And that ends this video.